Around 252 million years ago, Earth experienced something that makes every other extinction event look mild by comparison. 96% of marine species vanished. 70% of land vertebrates disappeared. The planet became so hostile that scientists call this period the Great Dying. This wasn't a quick asteroid impact like the one that killed the dinosaurs. This was something far more terrifying because it was slow, relentless, and touched every corner of the globe. Before we dive into the catastrophe itself, you need to understand what Earth looked like when everything was still intact. The Permian period stretched from roughly 299 to 252 million years ago, and the planet during this time was almost unrecognizable compared to today. All the continents had fused together into a single massive landmass called Pangaea. Imagine taking every modern continent, smashing them together, and creating one enormous supercontinent that stretched from pole to pole. That was Earth's geography for millions of years. This configuration created extreme climates that most modern organisms would find impossible to survive. The interior of Pangaea, thousands of kilometers from any ocean, became a scorching desert. Without nearby water to moderate temperatures, these inland regions experienced brutal heat during summer and freezing cold in winter. Coastal areas remained more temperate, but the sheer size of Pangaea meant that vast stretches of land received almost no rainfall. Seasonal monsoons would arrive with devastating force, then disappear for months, leaving the landscape parched and cracked. The oceans surrounding Pangaea, collectively called Panthalassa, covered everything else. On the eastern side of the supercontinent, a large bay called the Tethys Sea cut inward, creating a somewhat more sheltered marine environment. But even the oceans weren't stable. Sea levels fluctuated dramatically throughout the Permian, exposing and then flooding continental shelves repeatedly. These changes stressed marine ecosystems that had evolved over millions of years to expect certain conditions. Life had adapted remarkably well to these harsh conditions, though. Synapsids dominated the land, and these weren't dinosaurs. They were the ancestors of mammals, though they looked nothing like the mammals we know today. Picture creatures like Dimetrodon, with its distinctive sail-like back, or the massive herbivore Moschops, built like a barrel with stubby legs. These animals had developed strategies to cope with Pangaea's extreme temperatures and limited resources. Some regulated their body temperature through behavioral adaptations. Others had developed more efficient metabolisms. In the oceans, life thrived despite the challenges. Coral reefs built by organisms called rugose and tabulate corals created complex ecosystems. Brachiopods, shelled creatures that look superficially like clams but are actually completely different animals, covered the seafloor in dense colonies. Trilobites, those iconic armored arthropods that had survived for hundreds of millions of years, still crawled along the bottom, though their diversity had declined from earlier peaks. Ammonoids, spiral-shelled relatives of modern squid, hunted through the water column. The climate itself was in a precarious state. Atmospheric oxygen levels during the Permian were lower than today, possibly around 15 to 19% compared to our current 21%. This meant that animals couldn't grow as large as they had during the Carboniferous period, when oxygen levels had soared to 35% and insects the size of eagles buzzed through ancient forests. Carbon dioxide levels fluctuated throughout the Permian, sometimes spiking high enough to warm the planet significantly, then dropping again. But underneath this seemingly stable world, pressure was building in ways that nothing alive could detect. Deep beneath what is now Siberia, magma was accumulating in enormous chambers. Tectonic forces were arranging the pieces for the largest volcanic event in the last 500 million years. The continents, locked together in Pangaea, had created stress points in Earth's crust that were reaching their breaking point. Ocean chemistry was balanced in a way that left little room for error. What I'm about to describe isn't speculation. The evidence is written in rock layers across the planet, in isotope ratios that tell us about ancient temperatures, in fossil beds where entire ecosystems are frozen in their final moments, in chemical signatures that reveal exactly what happened to the atmosphere and oceans. Scientists have spent decades piecing together this story from hundreds of sites worldwide, and what they've found is more disturbing than any disaster movie. The extinction didn't start with a bang, it started with a crack. Around 252 million years ago, the Siberian traps began to erupt. These weren't typical volcanoes forming cone-shaped mountains. This was flood basalt volcanism, where magma poured out of massive fissures in the ground and spread across the landscape like water from a broken dam. The lava flows eventually covered an area roughly the size of modern-day Europe, in some places piling up more than 3 kilometers thick. But here's what made this volcanic event uniquely catastrophic. The magma didn't just erupt onto the surface. It burned its way up through layers of sedimentary rock loaded with coal, oil shales, and limestone. Each rock type released different gases when heated. Coal combustion pumped out massive amounts of carbon dioxide and carbon monoxide. Oil shales released hydrocarbons and toxic organic compounds. Limestone, when heated past certain temperatures, breaks down and releases even more carbon dioxide. The atmosphere began changing in ways that life simply couldn't adapt to fast enough. Carbon dioxide levels skyrocketed, and this wasn't just a matter of a few hundred parts per million. Some estimates suggest CO2 concentrations may have increased by thousands of parts per million over a period of tens of thousands of years. That might sound slow, but in geological terms, it was catastrophically rapid. Ecosystems need time to adjust, to evolve, to migrate. They didn't get that time. Temperature reconstructions from this period show a warming pulse that raised global average temperatures by anywhere from 5 to 10 degrees Celsius. In the already hot interior of Pangaea, this meant temperatures regularly exceeded 50 degrees Celsius. Most large animals can't survive sustained exposure to temperatures much above 40 degrees. Their proteins literally begin to denature. Smaller organisms could burrow underground or hide in caves during the worst heat, but large synapsids had nowhere to go. The warming triggered a cascade of secondary effects that made everything worse. As temperatures rose, the oceans absorbed more heat. Warm water holds less dissolved oxygen than cold water, so oxygen levels in the ocean began to drop. Deep ocean circulation, which normally brings oxygen-rich water from the poles to the depths, weakened or stopped entirely. The ocean floor became anoxic, meaning it contained essentially no oxygen. Anaerobic bacteria that thrive in these conditions began producing hydrogen sulfide as a waste product. Hydrogen sulfide is viciously toxic. It's the compound that gives rotten eggs their smell, but in high concentrations, it attacks the respiratory systems of animals and can kill quickly. As anoxic zones expanded upward from the deep ocean, hydrogen sulfide began bubbling up into shallow waters and possibly even into the atmosphere. Imagine trying to breathe air that smells like rotten eggs and burns your lungs with every breath. That was becoming reality in many coastal regions. The ocean's chemistry was changing in another crucial way. As carbon dioxide levels in the atmosphere increased, more CO2 dissolved into the ocean, forming carbonic acid. This process, called ocean acidification, is happening today but at a much slower rate. During the Permian extinction, acidification happened so rapidly that organisms building calcium carbonate shells or skeletons couldn't keep up. The water was literally dissolving their protective structures faster than they could build them. Coral reefs, which had taken millions of years to establish, collapsed completely. The organisms that built them couldn't maintain their calcium carbonate skeletons in increasingly acidic water. When the reefs died, all the species that depended on them for shelter, food, and breeding grounds died too. This pattern repeated itself across every marine ecosystem. Brachiopods vanished in enormous numbers. Trilobites, which had survived multiple mass extinctions over 300 million years, finally met their end. Only a handful of species made it through. On land, the situation was equally dire but played out differently. As temperatures soared and rainfall patterns shifted dramatically, vegetation died back. Without plants to stabilize soil and maintain the water cycle, erosion increased. Rivers choked with sediment. Lakes dried up. The food chain collapsed from the bottom up. Herbivores starved first, then the carnivores that depended on them. Fossil evidence from this period shows a characteristic pattern. Diverse ecosystems with dozens of species suddenly give way to sparse assemblages dominated by just one or two hardy species, then even those disappear. The extinction wasn't instantaneous. Current evidence suggests the worst phase lasted somewhere between 60,000 and 200,000 years. That's a geological eye blink, but for the creatures living through it, it was generation after generation of decline, of watching their world become progressively more hostile. Some species might have survived for tens of thousands of years in isolated pockets where conditions remained barely tolerable, only to finally succumb as those last refuges failed. What I find most unsettling about the Permian extinction is how many different killing mechanisms were operating simultaneously. It wasn't just heat, or just acidification, or just oxygen depletion. It was all of them, plus factors we probably haven't even identified yet, all working together to make the planet nearly uninhabitable. Life was being squeezed from every direction at once, with no escape route. And yet, somehow, life survived. Not most life. Not even a significant fraction of life. But enough. In the aftermath of the extinction, Earth was left with a biological blank slate. The survivors were mostly small, tough organisms that could tolerate extreme conditions. They inherited a planet that had been emptied of competition. What happened next would determine the entire future trajectory of complex life on Earth, including eventually us. The survivors faced a world that barely resembled the one their ancestors had known. Imagine stepping outside and finding that 90% of everything familiar had vanished. The landscape was sparse, strange, eerily quiet. This was Earth in the earliest Triassic period, roughly 252 million years ago. The recovery wasn't immediate. For the first million years after the extinction, ecosystems remained incredibly simple. Fossil beds from this time show what scientists call disaster fauna, assemblages dominated by just a few opportunistic species that could tolerate harsh conditions. One organism in particular became absurdly common, a small shrimp-like creature called chlorea that appears in massive numbers in early Triassic rocks worldwide. Its abundance suggests oceans with very low oxygen and limited food sources, conditions where generalists that could survive on almost anything had a massive advantage. On land, a similar pattern emerged. Lystrosaurus, a stocky herbivorous synapsid about the size of a pig, became perhaps the most successful land vertebrate of all time in terms of sheer dominance. Some fossil sites from the early Triassic are composed almost entirely of Lystrosaurus remains. It's estimated that this single genus may have comprised 95% of all land vertebrates for a period. That level of dominance is unprecedented. It suggests an ecosystem so simplified that normal competitive dynamics had broken down completely. But Lystrosaurus had traits that made it perfect for the post-apocalyptic world. It was relatively small, which meant lower food requirements. Its teeth were adapted for eating tough, low-quality vegetation, the kind of scrubby plants that colonize disturbed ground. It could probably dig burrows to escape temperature extremes. And crucially, it had a sprawling posture and physiology that allowed it to function in low oxygen conditions. While more active animals were suffocating, Lystrosaurus just kept plodding along. The early Triassic climate remained brutal. Global temperatures stayed elevated for millions of years. Some climate models suggest average temperatures were 6 to 8 degrees Celsius higher than today, with equatorial regions potentially reaching 50 degrees or more. At those temperatures, large animals physically cannot survive without sophisticated cooling mechanisms. Heat stroke becomes inevitable. This explains why the surviving animals were predominantly small. Large size, which had been an advantage in cooler Permian climates, became a death sentence. Recovery happened slowly, in pulses. The fossil record shows several false starts where biodiversity began increasing, only to crash again. These setbacks were likely caused by recurring environmental stress, volcanic eruptions that continued sporadically, or climate instability as Earth's systems struggled to reach a new equilibrium. Each setback reset the recovery process, eliminating newly evolved species and giving advantage once again to the hardy generalists. Around 5 million years into the Triassic, things finally began to stabilize. Oxygen levels crept back up. Ocean chemistry gradually normalized. Terrestrial ecosystems developed more complex soil structures as plants recolonized. And with stability came opportunity. The evolutionary experiments could begin. This is where the story gets interesting, because the survivors weren't just rebuilding what existed before. They were creating something entirely new. The dominant land animals of the Permian had been synapsids, the group that would eventually give rise to mammals. But synapsids had been devastated by the extinction. While some like Lystrosaurus survived, the group as a whole was greatly diminished. Another group saw their opportunity, the archosaurs. Archosaurs were reptiles, but a specific lineage distinct from the reptiles that would become lizards and snakes. In the Permian, archosaurs have been relatively minor players. After the extinction, they began diversifying rapidly. Early Triassic archosaurs were mostly small, quick carnivores that walked on all fours. They had certain advantages: a more efficient respiratory system than most other reptiles, an upright gait that was more energy efficient, and in some lineages, possibly even a form of warm-bloodedness. By the Middle Triassic, archosaurs had split into several distinct lineages. One branch would lead to crocodiles. Another would lead to pterosaurs, the flying reptiles. And one branch, the dinosauromorphs, would change everything. But we're not there yet. First, the world had to become strange. The Middle Triassic produced some of the weirdest creatures in vertebrate history. Without established ecological structures, evolution was experimenting wildly. Tanystropheus had a neck longer than its body and tail combined, possibly for snatching fish from the water while keeping its body safely on shore. Chaeravipteryx had enormous hind legs with flight membranes, a body plan never seen before or since. Longisquama had bizarre elongated scales along its back that some scientists think might have been precursors to feathers, though this remains controversial. The oceans weren't being left out of this evolutionary free-for-all. Ichthyosaurs appeared, reptiles that returned to the sea and evolved into forms remarkably similar to dolphins, complete with streamlined bodies and fish-like tails. Some species grew to enormous size, over 15 meters long. Nothosaurs developed, semi-aquatic predators that hunted in coastal waters. And in a twist nobody saw coming, some groups of marine reptiles developed live birth rather than laying eggs, a necessary adaptation for a fully aquatic lifestyle. Meanwhile, on land, the first true dinosaurs were emerging. They appeared around 230 million years ago, during the Carnian stage of the late Triassic. The earliest dinosaurs we know of, creatures like Heterosaurus and Eoraptor, were relatively small, between 1 and 3 meters long. They were bipedal, meaning they walked on 2 legs, which was unusual at the time. Most large animals were quadrupedal. This bipedal stance freed up their forelimbs for grasping prey and gave them speed advantages. But here's the thing that surprises most people. Early dinosaurs were not dominant. They were uncommon members of ecosystems still ruled by other archosaurs and various synapsid holdovers. For the first 15 to 20 million years of their existence, dinosaurs were minor players. The Triassic world belonged to different creatures. The true rulers of the late Triassic were the Rauisuchians, enormous predatory archosaurs that could reach lengths of 6 to 9 meters. They looked somewhat crocodile-like but walked upright on 4 legs and were purely terrestrial. Postosuchus and Saurosuchus were apex predators that would have made early dinosaurs look like snacks. Alongside them, Aetosaur, heavily armored herbivorous archosaurs, filled ecological roles similar to later armored dinosaurs, even though they weren't closely related. So why did dinosaurs eventually take over? The answer involves another catastrophe. Around 201 million years ago, at the boundary between the Triassic and Jurassic periods, Earth experienced another mass extinction. This one wasn't as severe as the Permian event. It wiped out perhaps 75% of species rather than 95%, but it was devastating enough to completely restructure ecosystems. The cause appears to have been massive volcanic eruptions associated with the breakup of Pangaea. As the supercontinent began splitting apart, enormous volumes of lava poured out across what's now the Atlantic Ocean. The Central Atlantic Magmatic Province, as it's called, was one of the largest volcanic events in Earth's history. Once again, carbon dioxide flooded the atmosphere. Temperatures spiked. Ocean chemistry went haywire. And once again, the survivors weren't necessarily the strongest or largest, but those with the right combination of traits for the new conditions. The Rauisuchians, those dominant Triassic predators, went extinct. The large herbivorous synapsids disappeared. Many of the weird experimental forms vanished. But dinosaurs made it through, and not just barely, they thrived. What gave dinosaurs the edge? Several factors probably contributed. Their efficient respiratory system, which involved air sacs that allowed continuous airflow through the lungs, similar to modern birds. This meant they could extract more oxygen from each breath, crucial in potentially low oxygen conditions. Their upright posture, which was more energy efficient for sustained activity than the sprawling gait of many competitors. And possibly their relatively fast growth rates, which allowed populations to recover quickly after disruptions. In the aftermath of the Triassic-Jurassic extinction, dinosaurs rapidly diversified and grew larger. The early Jurassic saw the emergence of the first giant sauropods, long-necked herbivores that would eventually become the largest land animals ever to exist. Theropods, the carnivorous dinosaurs, evolved into a spectacular array of forms. And a third major group, the Ornithischians, developed specialized herbivorous adaptations. Within 10 million years of the extinction, dinosaurs have become the dominant large animals on every continent. Their reign would last for 135 million years, an almost incomprehensibly long period of time. During that span, they would evolve into thousands of species, from chicken-sized hunters to 100-ton giants, from Arctic-dwelling forms to desert specialists. But their success was built on a foundation of catastrophe. Without the Permian extinction emptying the world, without the Triassic-Jurassic event eliminating their competitors, dinosaurs might have remained minor players forever. The history of life is written as much by what dies as by what survives. And so the age of dinosaurs began in earnest, not with a bang but with a quiet expansion into empty space. The early Jurassic world, roughly 201 to 174 million years ago, was dramatically different from what came before. Pangaea was still mostly intact but beginning to fracture. The climate was warm and humid across most of the supercontinent, with no polar ice caps. Sea levels were rising as the planet warmed, creating shallow inland seas that fragmented the land masses. In this greenhouse world, vegetation exploded. Ferns carpeted the ground. Conifers towered overhead. Cycads and ginkgos filled the middle layers. For herbivores, it was an all-you-can-eat buffet, and the sauropods took full advantage. These long-necked giants developed a body plan so successful it would persist, with variations, for the rest of the Mesozoic. Their small heads sat atop necks that could reach high into the canopy or sweep low across the ground. Their massive bodies housed enormous guts capable of processing huge quantities of low-quality plant material. And their pillar-like legs supported weights that would crush most other vertebrates. But here's what's fascinating about sauropod evolution. They didn't just get big. They got big in very specific ways that solved particular problems. Their necks contained numerous lightweight vertebrae with hollow spaces, air sacs that reduced weight while maintaining strength. Their respiratory systems were incredibly efficient, pulling oxygen through the lungs in one direction rather than in and out like mammals. And they laid eggs, which might seem trivial until you consider the alternative. A mammal giving live birth to a baby sauropod would be physically impossible. The mother would die. Eggs solved this problem elegantly, allowing even the largest dinosaurs to reproduce without the constraints that limited mammalian size. The theropods, meanwhile, were exploring different strategies. While sauropods went big and slow, theropods remained relatively agile. Early Jurassic forms like Dilophosaurus were already showing the basic theropod template: bipedal stance, grasping hands, sharp teeth. They weren't the apex predators yet, not the way later forms would be, but they were competent hunters filling various niches. Then something unexpected happened. Some theropods started shrinking. This seems counterintuitive in a world trending toward gigantism, but evolution doesn't follow our expectations. Smaller theropods could access different food sources, hide from larger predators, and reproduce more quickly. Some began developing feathers, probably first for insulation or display, only later for flight. This lineage would eventually lead to birds, but we're getting ahead of ourselves. The Middle Jurassic, from about 174 to 163 million years ago, is frustratingly poorly known. The fossil record from this period is patchy, leaving paleontologists with tantalizing glimpses rather than a complete picture. But what we can see suggests continued diversification. Sauropods were getting larger. The first stegosaurs appeared, those plated dinosaurs with tiny heads and huge bodies. And in the oceans, marine reptiles were reaching their own impressive sizes. It's worth pausing here to note what wasn't happening. Dinosaurs dominated the land, yes, but they never conquered the oceans or truly mastered the air during most of their reign. The seas belonged to ichthyosaurs, plesiosaurs, and later mosasaurs, none of which were dinosaurs. The skies were ruled by pterosaurs, flying reptiles that were cousins to dinosaurs but not dinosaurs themselves. This tells us something important about evolution. dominance in one environment doesn't automatically translate to dominance everywhere. Each realm required its own specialized adaptations. The late Jurassic, 163 to 145 million years ago, is when dinosaurs really hit their stride. This is the period most people picture when they think dinosaur. Enormous sauropods like Brachiosaurus, Diplodocus, and Apatosaurus roamed what's now North America. Allosaurus stalked them, a 9-meter predator with huge jaws and slashing claws. Stegosaurus defended itself with its distinctive back plates and spiked tail. And in what's now Germany, a small feathered dinosaur called Archaeopteryx left fossils that would later help scientists understand the dinosaur-bird connection. The Morrison Formation in the American West preserves this world in exquisite detail. Picture a landscape of braided rivers and floodplains, dotted with conifer forests and fern prairies. Sauropods move through in herds, stripping vegetation. Theropods followed, looking for weak or isolated individuals. Smaller dinosaurs scurried through the undergrowth. And overhead, pterosaurs wheeled through skies that had never known a bird. But scale can be deceptive. When we see museum skeletons or movie reconstructions, we're seeing the success stories, the animals that grew large and left impressive fossils. We're not seeing the thousands of smaller species that left fragmentary remains for no fossils at all. For every Brachiosaurus, there were probably dozens of chicken-sized dinosaurs we'll never know existed. The fossil record is biased toward big animals with hard bones in the right environments. Everything else is mostly invisible to us. The Cretaceous period, from 145 to 66 million years ago, saw dinosaurs reach their peak diversity. This wasn't because they were getting better at being dinosaurs. It was because the world itself was fragmenting. Pangaea had fully broken apart. Sea levels were extraordinarily high, creating more coastline and shallow seas than at any other point in Earth's history. Continents were isolated from each other, allowing evolution to proceed independently on different landmasses. This geographic separation led to spectacular diversity. In South America, massive carnivores like Giganotosaurus evolved, possibly even larger than Tyrannosaurus rex. In Africa, Spinosaurus developed a bizarre sail-backed body plan and semi-aquatic lifestyle. In Asia, the tyrannosaurs were beginning their rise to dominance. And in North America, the famous late Cretaceous fauna was assembling: Triceratops, Ankylosaurus, Pachycephalosaurus, and eventually T. Rex itself. The Cretaceous also saw the rise of flowering plants, angiosperms, which would fundamentally reshape terrestrial ecosystems. Before this, plant reproduction was slow and inefficient. Conifers, ferns, and cycads dominated. But flowering plants reproduced faster, grew more quickly, and formed more complex relationships with animals. They offered new food sources, fruits, nectar, and more nutritious leaves. Herbivorous dinosaurs adapted, developing sophisticated chewing mechanisms. Hadrosaurs, the duck-billed dinosaurs, had hundreds of teeth arranged in dental batteries that could grind through tough plant material. Ceratopsians had powerful beaks and shearing teeth. Ankylosaurs had fermentation chambers in their guts. These weren't simple animals mindlessly eating and reproducing. Evidence suggests complex behaviors, parental care in some species, possible migratory patterns, social structures, even potential territorial displays. We find bone beds with dozens of individuals of the same species, suggesting herding behavior. We find nests with carefully arranged eggs and evidence of adults returning to nesting sites. Some species show sexual dimorphism, different body features between males and females, hinting at complex mating rituals. By the late Cretaceous, roughly 80 to 66 million years ago, dinosaur ecosystems had reached a level of complexity comparable to modern ecosystems. There were small insectivores, medium-sized herbivores, giant browsers, pack hunters, and solitary apex predators. There were specialists and generalists, lowland forms and upland forms. In some environments, dinosaur diversity rivaled what we see in modern mammal communities. And they were still evolving, still adapting, still producing new forms. There's no evidence they were in decline before the asteroid hit. Some paleontologists have argued that dinosaur diversity was dropping in the final million years of the Cretaceous, but this is hotly debated and probably reflects biases in the fossil record rather than actual decline. The dinosaurs weren't old and tired. They weren't evolutionary dead ends waiting for extinction. They were thriving. Which makes what happened next even more shocking. An asteroid roughly 10 kilometers across, traveling at about 64,000 kilometers per hour, slammed into what's now Mexico's Yucatan Peninsula. The impact released energy equivalent to billions of nuclear bombs. It vaporized rock, created a crater almost 200 kilometers wide, and sent shockwaves around the planet. Within hours, debris was raining down globally, igniting fires across multiple continents. Within days, dust and sulfur compounds had blocked out the sun. Within months, photosynthesis had ceased almost everywhere. The dinosaurs, those magnificent animals that had dominated for 165 million years, died. Not all at once, and not all for the same reasons. Some starved when plants died. Others froze when temperatures plummeted. Many drowned in tsunamis or suffocated in toxic air. The large ones went first, unable to find enough food to maintain their massive bodies. The specialists followed, their narrow ecological niches collapsing. What survived were the small, the flexible, the generalists. Animals that could hide, that could eat almost anything, that could tolerate cold and darkness. And among the survivors, barely, were the birds. Birds are dinosaurs. Not descendants of dinosaurs, not related to dinosaurs. They are dinosaurs, the only lineage that made it through. Every sparrow, every pigeon, every eagle is a living theropod, carrying forward a heritage that stretches back to the Triassic. The asteroid didn't end the dinosaur story. It edited it down to a single surviving branch. But let's be precise about what survived. Not all bird groups made it. The Cretaceous sky was full of avian diversity, toothed birds, flightless diving birds, large terrestrial forms. Most died. What crossed the boundary were small, likely generalist species. Birds that could eat seeds, insects, maybe carrion. Birds that didn't depend on specific forest types or particular prey animals. In the immediate aftermath, with forests burned and food chains shattered, flexibility was everything. The early Paleocene, the period right after the extinction, was a drastically simplified world. Fossil sites from this time show ecosystems with far fewer species, simpler structures, less specialization. The recovery wasn't instant. For the first million years or so, life struggled. Ferns exploded across the landscape, a classic disaster response. They're fast-growing, spore-based, and thrive in disturbed environments. Pollen records show what's called a fern spike right at the extinction boundary, a sudden overwhelming dominance of fern spores in the geological record. Slowly, ecosystems rebuilt. Flowering plants returned, though the composition changed. Some Cretaceous plant families vanished entirely. Others that had been minor players became dominant. Animal communities reassembled, but with completely different caste lists. The niches that dinosaurs once filled, gigantic herbivores, massive predators, were now empty. And into that vacuum stepped the mammals. Mammals have been around almost as long as dinosaurs, originating in the late Triassic around 225 million years ago. But for the entire Mesozoic, they'd been bit players. Small, mostly nocturnal, eating insects and seeds and staying out of the way. The largest known Mesozoic mammal, Repenomamus, was about the size of a badger and possibly ate baby dinosaurs, but that was exceptional. Most were mouse-sized or smaller. Why were they so small? Probably because dinosaurs occupied all the larger ecological roles. There was simply no space. Any mammal that tried to get bigger would be competing directly with vastly more successful reptilian forms. So mammals stayed small, stayed hidden, and survived in the margins. Then the asteroid reset the board. Within 10 million years, an eye blink in geological terms, mammals exploded in size and diversity. By the early Eocene, roughly 56 million years ago, there were mammal predators as large as bears, herbivores the size of rhinos, and bizarre experimental forms that have no modern equivalents. Consider Androsarchus, known only from a massive skull found in Mongolia. It lived about 45 million years ago and may have been the largest mammalian land predator ever, possibly reaching a ton in weight. Or the Brontotheres, rhino-like herbivores with elaborate horns and head crests. Or the Encelodonts, sometimes called hell pigs, aggressive omnivores with bone-crushing jaws. The Paleocene and Eocene were periods of wild evolutionary experimentation. With so many niches empty, natural selection could explore options that would never have been viable in the Mesozoic. Some experiments worked. Most didn't. The fossil record from this time is full of short-lived lineages, creatures that appeared, diversified briefly, then vanished as better adapted groups replaced them. Primates emerged during this chaos. The earliest known primate fossils date to around 55 million years ago. They were small, arboreal, probably similar to modern tree shrews or small lemurs. Nothing about them suggested future dominance. They were one evolutionary experiment among thousands. But they had certain advantages. grasping hands with opposable digits, useful in trees. Forward-facing eyes providing depth perception, critical for judging distances when jumping between branches. Relatively large brains for their body size, though still tiny by modern standards. These weren't dramatic advantages. They didn't make primates dominant. They just made them viable in a particular ecological niche, the forest canopy. For tens of millions of years, that's where primates stayed. Up in the trees, eating fruits and insects, slowly diversifying. By the Oligocene, around 30 million years ago, there were monkeys and early apes. Still arboreal, still relatively small-brained, still just another group of mammals among many. The critical shift began much later, in Africa, probably around 7 to 6 million years ago. Climate change was driving it. Global temperatures were dropping, forests were fragmenting, and grasslands were expanding. Some primate populations found themselves spending more time on the ground, moving between scattered forest patches. Walking upright on two legs, bipedalism, offered advantages in this environment. It freed the hands for carrying food or tools. It allowed seeing over tall grass. It was more energy efficient for long-distance travel than quadrupedal knuckle walking. Natural selection began favoring individuals who were better at walking upright. This is where the human lineage begins to separate from other apes. Not with intelligence. Not with tool use. Those came later. The first defining characteristic of our lineage was simply the ability to walk efficiently on two legs. Fossils from this period are rare and fragmentary. We have Sahelanthropus, dated to about 7 million years ago, known from a partial skull. We have Ororan, about 6 million years old, known from a few bones suggesting upright walking. We have Ardipithecus, around 4.4 million years ago, definitely bipedal but still spending time in trees. These weren't humans. They were apes experimenting with a new way of moving. Their brains were still chimpanzee-sized, around 350 to 400 cubic centimeters. They probably didn't make complex tools. They lived in small groups in woodland environments. If you saw one, you wouldn't think that's going to evolve into something that dominates the planet. You'd think, interesting ape. Around 4 million years ago, a new genus appeared, Australopithecus. These were the first hominins to really commit to terrestrial life. They walked upright habitually, though their arms were still relatively long and they probably still climbed trees for safety and food. Their brains were slightly larger than earlier forms, maybe 400 to 500 cubic centimeters, but still well within ape range. The most famous Australopithecus fossil is Lucy, discovered in Ethiopia in 1974. She lived about 3.2 million years ago, stood roughly 1.1 meters tall, and weighed perhaps 30 kilograms. Her skeleton shows clear adaptations for bipedalism, a bull-shaped pelvis, a knee angle that kept her center of gravity over her feet, a forward-positioned foramen magnum where the spine connects to the skull. For over 1 million years, various Australopithecus species lived across eastern and southern Africa. They were successful animals, well adapted to their environments. But they were still fundamentally apes. They didn't build shelters, didn't control fire, didn't create complex tools. Then, around 2.8 million years ago, something shifted. We start finding stone tools in the archaeological record. Not sophisticated tools, just rocks deliberately chipped to create sharp edges. But this was new. This was technology, however primitive. The first species clearly associated with stone tool manufacture is Homo habilis, which appeared around 2.4 million years ago. Habilis means handy man, and it's an appropriate name. Their brains were larger than Australopithecus, around 600 cubic centimeters, and their hands show better precision grip. Still, Homo habilis wasn't dramatically different from earlier hominins. They were still small, probably around 1.3 meters tall. They probably still spent time in trees. Their tools, the so-called Oldowan industry, were simple, sharp flakes struck off larger rocks, useful for cutting meat or processing plant materials. What matters is the principle. Using tools isn't unique to humans, many animals use tools. But making tools, deliberately modifying objects to create something more useful, that's rarer. And passing that knowledge down through generations, that's rarer still. With stone tools, we see the first glimmers of culture, information transmission beyond genetics. Around 2 million years ago, a new species emerged, Homo erectus. This is where things get interesting. Erectus was taller, averaging around 1.8 meters. More importantly, their brains were substantially larger, ranging from 800 to over 1,000 cubic centimeters. They made more sophisticated tools, the Acheulean hand axes, carefully crafted teardrop-shaped implements that required planning and skill. And Homo erectus walked out of Africa. Fossils have been found in Georgia, China, Indonesia. This species, or closely related forms, spread across the Old World, adapting to environments from tropical forests to temperate grasslands. They likely controlled fire, though the evidence is debated. They hunted cooperatively. They may have had basic language. Homo erectus was successful. Incredibly successful. They lasted for over 1.5 million years, far longer than our species has existed so far. They were the first truly cosmopolitan hominin, the first to demonstrate that our lineage could adapt to wildly different environments. But they weren't modern humans. Their brains, while large, were still structured differently. Their skulls were thick-boned with prominent brow ridges. Their bodies were robust, built for strength rather than endurance running. They made the same basic tool types for hundreds of thousands of years with little innovation. What happens next is complicated. Between about 800,000 and 300,000 years ago, Homo erectus populations in different regions began diverging. In Africa, they evolved toward forms with more gracile skeletons and larger, rounder skulls. In Europe and Western Asia, they evolved into Neanderthals. In Eastern Asia, they became Denisovans and possibly other groups. The human family tree during this period wasn't a straight line. It was a bush, multiple species existing simultaneously, sometimes in the same regions. And they didn't stay isolated. Genetic evidence shows they interbred when they met. Neanderthals appeared around 400,000 years ago in Europe and Western Asia. They weren't brutish cavemen. That's Victorian mythology. Neanderthals had brains as large as or larger than modern humans, averaging around 1,400 cubic centimeters. They made sophisticated tools, controlled fire expertly, built shelters, buried their dead with apparent ritual. They survived ice ages in some of the harshest environments on Earth.